Hey, I'm Ben Brown, or nordus-mocwyl on Urbit. Part 2, last time we kind of defined the problem space that Urbit is a solution for. We get to talk about Martian computing today. And we talk about some wild ideas of what a computer could be. This video may contain a bonus, and I'm about to record that bonus. So enjoy the video. And that kind of brings me to Martian computing, or Martian computers. There's a thought experiment that's at the conception of Urbit. And that is, let's think 500,000 years into the future. Humanity's still around. They're naturally living on Mars, probably terraformed into a beautiful second Earth. These Martians, these humans, obviously have computers running the things they do. What do those computers look like? They will undoubtedly have computers, but they will guaranteed look nothing like what we have, because if you take our current computers in the way that they're networked together and you drag it 500 years into doing the exact same thing, like that thing is going to be an absolute mess. Maybe I did need to talk about the nodes of the network. Why is our network like this? Like this is today. Today, where there's only so many computers serving other computers that just go check up with it. The reason it's that way is because in order to run one of these things, you could get paid $100K a year as a manager of a server. This is lowballing it. And the reason that you can make tons of money is because the amount of stuff you need to know to manage it is just enormous. It is a huge task to comprehend what you need to know to manage that thing. Even when you do know it, the amount of BS time that has to go into fixing problems and redoing things, it's a thing people don't want to do. It's too hard and people don't want to do it. Where ideally everybody is running these full things on the network, it's like, no, we just changed to this other model. This is the client-server model. A small handful will actually do what computers do. The majority will just check up on them. Because this is easy and that's hard. Martian computers, they're not going to work that way. They're going to have the best of whatever we dreamed up for that whole scenario. And if we can pull that aspiration into our present, into our today, then we can not waste time building things on a system we can't imagine would exist in 100 years or 30 years. There's just not a sense of longevity. How can we coax that thing into our present, make that ideal a reality? This isn't my thought experiment. This is the founder of Urbit thought experiment. There were some conclusions that were made. Things like, it just needs to be radically simple. The computer itself, it should be possible for one person to completely understand it. That whole crazy server that requires an endless list of understanding things and the patience of somebody getting paid $200K a year to deal with it, that is not simple. It's way too complicated. A Martian computer is going to be something that you can understand when you're done with high school. And in that, we'll end up talking about a computing model called nock. Another characteristic, it needs to be enduring. If it's a general purpose thing that can do whatever you want and it's sitting on the world's peer-to-peer network, it's going to be really valuable and you don't want it to break down. A computer that can last hundreds of years into the future, can be passed down to grandchildren. This is an enduring computer. That's a wild statement to make. You can't do it with a computer today. The Martian computer, the thing that we're aiming at, you can totally do that. That's there. In talking about an enduring computer, we will talk about Kelvin versioning, portability, and the thin waist. I'll draw a little hourglass here. Let's tackle enduring for a second. One of the key things here is this portability. You want to hand everything about your life, your family business to your grandchild in the little key fob, a little computer, and it's like, this is everything. This does everything. This is ours. Here you go. You have a general purpose machine. It's sitting on the global peer-to-peer network. This thing is going to be valuable out the wazoo. It's just going to mean everything to you. Sentimentality, money-wise, you wouldn't be able to put a price on how valuable this thing is. Beautifully cut diamonds, right? You don't want it to be landlocked on one particular device. You don't want it to be only on your phone. You don't want it to be only on your computer. You don't want it to be only on the server farm rack thing. Like, you want that thing to be able to move from one space to the next space. You want it to be completely portable. The family jewels. How great. The way this is achieved is Urbit, instead of being like an actual physical machine, like an actual computer that's flipping, buzzing, taking electricity, it does a really common thing of being a virtual machine. It's not running directly on your computer. It's running on top of your computer in software that defines what it is and how it works. And being a virtual machine means that it's possible to take it from one space to another. That's a relatively simple way of saying it. I'm going to use my drawing of a server. I guess it's a thought bubble. There you go, VM. It's not this part with the plug. It's dreamed up, this virtual machine. That's where an Urbit is, and that allows you to take it to different places, which is why we should talk about thin waist. We already discussed portability. That'll actually explain this bottom part of the thin waist. Urbit has placed itself in a spot. That's what this little pinch point in the waist is. Like, that's a unique opportunity in computers to accomplish really both of these things, radical simplicity and creating a computer that endures. So let's explore that a little bit more. Nothing goes to waste. Always eating that buffalo. So the way that the thin waist is, the wide base part, this is the hardware here. As we make computers, like we went from computers that are the size of a house to a computer that can sit on your desk, into your pocket, then there'll be quantum computers. We don't know what shapes those are going to take. The hardware is this world of infinite possibility. And so if your strategy of making a computer is have it talk directly to the hardware, tell it what to do and how to compute, then that means everything that you write above it is going to have knowledge of the hardware, in the new hardware, in the fact that it changes all the time. But if everything that you care about, if the part that matters to you as a human is actually defined in software, as long as somebody makes this connection down here, your computer can stay exactly as it is. The virtual machine is in a unique position to do that. That's not unique to Urbit. If you make a computer that's completely defined in software and agnostic, totally doesn't care what it's running on, you have the ability to run it on anything as long as you have a place to plug it in. Top half, this is all the things that you would build on top of the virtual machine. This is yet another infinite space. All the programs you and anybody else would think to make on your general purpose machine. It is everything. After the Martians created this, they spent 500 years building everything on top of it. That whole space, what you could possibly build is a huge infinite space as well. What would you do with a computer? Infinite possibility on top, infinite possibility on bottom. That leaves what are you going to do here? A virtual machine allows a cushion between that virtual machine and machinery underneath it. Let's now talk about how you can actually have the thin waist so that all the infinite possibility of what you could do with a computer can actually rest on one thing that can always stay the same and be radically simple and understood by a person. Let's start with Kelvin versioning, because I think it's another one of those mind-blowing ideas, like giving your grandchild your computer. Kelvin versioning. Whenever you make something that you expect other people to build on top of, a very polite thing to do, if you're going to change that, is to give it a version number so people can figure out if there's something that you did in the new version that broke what they were trying to build on top of it. Typical versioning goes version 1.00. A little bit later, 1, make a little change, 2, let's do kind of a bigger change. Here's the 1, 0. And it's like, let's really overhaul it. People are going to need to pay attention because it might break everything. We're going to release a version 2. And we'll make little patches. People complained about something. Okay, let's patch it. It has the potential to go infinite. Your version of your software, as you tick out, it could just keep on going. What if you gave yourself a certain number of versions, like 500? You release a new one, you let them know, like, hey, we're at version 499. You make another change, you make 200 more changes, 298. You make 200 more changes, you're at version 98. You make 90 more changes, and you're on version 8. And then you're thinking, I have very few more chances to get this right. Because when I finally tick over to version 0, that is it. It is locked away in the hypercube, frozen. It becomes a completely frozen block of ice. I'm showing this ice melting, but it wouldn't be how it would go. Starting with 500 chances, there's lots of changes that could be happening, but like as you tick through, refining, it can get colder and colder, less things happen, less jiggliness happens. And ultimately, you will come to a point where it's like, this will not change. This is the unique opportunity here at the thin waist. You can't dream up the possibility of making something that doesn't change unless you have a thin waist. Otherwise, this space is as infinite as any of the other spaces. Kelvin inversion is possible in this scenario. Right now, your Urbit, if you have an Urbit, there's some parts of your Urbit that are at 411K, and there's some parts of your Urbit that are at 4K. Some parts were built a long time ago, and they've already gone through lots and lots of cooling. There are newer things that are cooling on top of it. If something changes, all the things that are built on top of it will have to also tick down because that's a breaking change, and everything cools in this kind of way. Yeah, so it's Kelvin versioning. It's totally different. You could make something that just stays there forever. Let's talk about how a Martian computer is vastly more simple than current computers. One of the targets for this is every responsible adult should be able to understand it all of the computer, if they wanted to be able to manage it with a ease that is much, much lower than the value of actually having and running that thing. The exact opposite of the Santa Claus list long credentials needing to run one of these servers. The brutal amount of boring time required. How do you do that? Reduce the time as much as you can. Start chomping off all these requirements of things that you need to know. Having a simple computer, it's going to help that you can understand just the virtual machine part of it and not have to understand the underlying machine. Maybe it'll help in understanding the simple computer. The thing to do is return to this bottom part of the virtual machine guy. Okay, I'm going to borrow that for this example here. How do you make a complicated computer? How do you make an absolute mess out of a computer? One of the ways is by having like hardware that has all kinds of capabilities. Let's represent that with some circles. These are like all the different capabilities of a computer. Hey, we figured out how to make movies faster. We added this thing. We figured out how to do encryption a little bit quicker, so we added this. We figured out how to do the math of compression and decompression a little bit faster. We've added this stuff, but here's your operating system. An operating system is the thing that you touch as a user. This is how you tell the computer to do something. If that operating system has to know about this thing, has to know about this and this thing, all the things that are built on top of it, they need to remember about that thing, and this thing, and that thing. You're going to have a big old mess on your hands because what's going to happen, we're going to upgrade this sucker, making it bigger and putting a big old 2 on it. We're going to add a couple more things. And this little system is like, oh my gosh, I really want this thing. That thing would be awesome. But the operating system has to know about that. And then this has to connect to that. They need to update it to version 2 because the hardware just changed so that this person can update it so they can go to version 2. And then somebody shows up and they have the old version and they don't have that. And you're like, shoot, I need to make sure my program is backwards compatible to operate without that thing there. That's how you have a big old mess, right? That's a complicated mess. Don't want that. And you have people getting overpaid because they do a whole bunch of nasty work that they don't want to do. And it's hard to be qualified to do it. That's called being a software engineer. And people are realizing that. How do you make this operating system, this virtual machine, interchangeable? Here's what you do. We already know the answer. The operating system should not care what the hardware is capable of. Everything that you build on top of it will take care of itself once you do that. Now you've got a nice little thin waist. It's portable and it has the potential of being enduring. What does it look like to create that insulation? What are the requirements or what do you need to do? One of the things you'll have to do is inside of that virtual machine, you're going to need to define how to compute stuff. In this scenario, ultimately the definition is in the hardware. That tells you how you're computing. But the virtual machine, if you're going to separate it from the hardware, it needs its own definition, its own rules of how to compute stuff. What is computing? What is compute? What's going on here? Computing is, hey, I have a thing here. Go and grab it. Once you know about it, grab this thing over here too, add them together, and put them here. Computing involves finding out where something is, take that and this, do something, and put the result here. A part of computing and having a complete definition is that has an address, it's at 1, and this is at 2. I have instructions on what you need to do at 3, and the place that I want to put it is here. Does that make sense? So imagine this little collection of spaces, here's, different spots in the computer. This is necessary for the computer to get orientation. It has to know where it is. You know where you are in computing. You need a left, a right, north, south, west, east. You have to get oriented in some kind of way. Okay, I have this at here, an action called add here, and I have a spot that's currently filled with 0. I have another thing here. I can tell the computer, take the thing at 1, do the thing at 2, add that with the thing at 4, place it at 3. It overwrites here in slot 3, and slot 3 is your answer. That's computing. That's what a computer's doing. And then you can interpret 99 to be like win lottery, or 99 is move robot arm, whatever you want it to be in the real world. You turn off AC. It's like whatever you need it to be that can be attached to it. That's computing. Hardware is going to have a bunch of instructions, so add stuff together. All these little bells and whistles inside of there are going to be special little cases of how to do things, and that grows over time. There's no limitation to how many of these things the hardware might create. Each one of these things becomes an instruction that you need to tell the computer to know about in order to do the computing in the most efficient way possible. But Urbit has brought up the definition of compute into itself. And so it defines computing, and computing, it's universal, it's transferable. If you compute something in one way, it's completely equivalent to computing it in a separate way. It doesn't matter if you use the decimal system, it doesn't matter if you used note cards, punch cards, that computing is the exact same as what you would type into a quantum computer or what you would be changing in your brain. Same thing, just different performances. With the virtual machine, it's defined its own compute. The name of that set of possible instructions in Urbit is nock, Urbit's definition of compute. Counter to this style, which can breed 600 to 30,000 instructions, nock only has 12 options. That includes the addressing. Something is here. Here's how you do something. It has add +1, and it has the question, is it equal? There's the other one that's branch. It's optionality. I want you to do one of two things. Either do this computation or do this computation. That can be determined by another thing. That's branching. That's the basics. That is, nock goes through these 5 things. So we're here in the docs. It goes through nock. This is pseudocode. It's not actually what you would run, but it is the concept of this particular definition of how you compute something. Notice, nock is actually the thing that is 4 Kelvin. It is practically frozen. 4 more attempts. If this thing needs to change, 1, it has like huge impact on everybody, and 2, it's just not likely. The definition of nock follows as such. When I say there's a this and there's a that, it simplifies it by saying it's just a natural number, which is only positive numbers, no negative numbers and no decimals, just a natural number. You can have them together in a tree. The slash is how to do a here moment, where it's like, I want you to go here. Here's the landscape, here's the world. That slash is the orientation. We have the add 1 to it, and we have the check to see is equal, and then we have the branch. That's what this question mark is. This section is like about how you do something. How do you take something from here, take an action, and then do the next thing? That defines compute. It's very small. You can fit it on a t-shirt. That is the TM trademark. Fit it on a t-shirt. Eventually they get dropped down into explaining the instructions. You have 0, you have 1, you have 2, you have 3, you have nock 4. This is how they say it. Nock 5, nock 6. Nock 7, nock 8, nock 9, nock 11, and because we had nock 0, we have 12. I only really went over 5 because that's all you really need. Instructions 6 through 11. They combine the top 6 to make things a little bit easier. Yeah, so that's nock. When you have a full set of a computing definition, this is called Turing complete. It means it can do anything and everything. One Turing complete machine is equivalent to another Turing complete machine. This gigantic set of all these different instructions that a hardware machine is privileged to be able to utilize is equivalent. It is the exact same as this set of 12. Either rummage through 3,000 ways of computing something, all the different instructions that you could possibly give the hardware, or you can like master 12, get the exact same thing. This is what lies right here at the thin waist. This part here, it's software and it does have to integrate with the hardware, but you only have to teach it 12 things. Here's the 12 ways you're going to compute it. The hardware changes underneath us. We just had to explain 12 things to get the exact same computer. There's also special cases called jets, and boom, we solve this. With Kelvin versioning, that solves this part. So when somebody builds directly on top of the virtual machine right there, it doesn't change. This program, as long as it doesn't depend on anything else, it's going to run regardless of everything happening underneath it. And that's how you give your computer to your grandkids. Okay, that's what I wanted to say about Martian computing. Looking into the future, humans are on Mars. They got computers. They ain't like what we got today. How do we pull that into where we are? Portability comes in and making it a virtual machine, making the thin waist, having the Kelvin version solidify everything. And its own definition of computing is just so much more comprehensible for as many people as possible. That is the goal. Let's return to my original question. Is Urbit still relevant? Well, now we can build up forever without worrying about it collapsing, worrying about the bottom piece of a Jenga tower moving. Somebody just kind of yoink, and then it seems like a yes. How long do you build sandcastles until you make a castle made out of stone? Eventually you figure out how to have a firm foundation to build on. That seems good. We also had this AI, right? Like, okay, yeah, computers are a mess, but like AI, wave some hands, fix. Isn't it going to make all this stuff easier? And there is a chance whenever we have these complicated servers with all the things that you have to know about it and like all the time it takes to run and manage it. There's places where like you can plug AI into understanding some of this stuff, and maybe we get to the point where the AI can make the OS system on the fly. It just keeps on rewriting itself to understand the hardware. And then the AI can also manage all the different programs, and it just keeps on rewriting everything. But like, I can't help but wonder, and this is a little fanciful, if we make an actual person out of an AI, like a synthetic person, I have a feeling they're going to decide this isn't worth all the power. If you were to talk to a rational AI, I would be blown away if an AI person isn't like, that's a great idea. Why wouldn't they? Is Urbit still relevant in 2025? Yeah, it'll be a part of what I'm interested in and what I'm paying attention to. I have ideas of things I want to build, and I don't want to build sandcastles. I'm not sure how hard I'll be going on it, but I want to see it happen. It's good. Hey, welcome to the bonus video. I'm going to return to my example of my sister had a video on her phone. I needed to get it to my computer. Trying to make that happen was painful and difficult and required us to essentially bolt on the peer-to-peer connection. How that went down kind of illustrates a peer-to-peer network has an inherent jank. There's just a little jankiness to it. When we finally got this peer-to-peer connection, I had to keep on texting my sister like, hey, I got to 25%, but it stopped. What happened? Oh, my phone turned off. Okay, turn that back on. Okay. It's like it started off where it left off. Cool. We get to 50%. Hey, it stopped. What happened? Oh, dang it. I'm sorry. I'm so sorry. Get to 75%, 80%. It dies. I had to constantly be poking at her like, hey, keep up your end of the connection. I need you to keep this thing going. In a peer-to-peer network, you have like people, individuals that are operating the computers that are going to be on that network, right? Individual people are in charge of this. Are individual people 100% reliable? Do they always have their computers on? It's quite possible, and in fact, inevitable, that some of these things inside the network, when you try to reach them, they're just not going to respond, not be there, or take a long, long time. That means like peer-to-peer networks, all of them, no matter which one they are, if people are running the whole thing, there's jank in the system, and it's just there. It's not going to end. What's wrong with that jank, and can our desire for a peer-to-peer network overcome the fact that that will always exist? I mean, there's a few alleviations. You can do this kind of thing where you let somebody else run your peer-to-peer network. Like they'll have a collection of these. They will run those for you, but it's also like kind of weird. It doesn't fit all the ideology. This scenario is a hosting provider. They'll take your peer-to-peer networks and they'll make sure that they are always on and always connected to the internet. That is a service, and it feels more like what we expect from a modern app. Data centers are set up in a way that like talking to them and getting things back is really fast. And they pride themselves in like the uptime of those servers. The only other way to get rid of the jank is a social solution. When you run this thing, you have to understand, put it in a place, like give it a power backup, give it a physical internet connection. This helps when people want something from you to feel like it's responsive. In the same way, being like, hey, everybody else, you need to be patient and slow your roll. Peer-to-peer network, it has that jank. You can't really do anything about it. The only thing that you really can do is manage expectations right up front. If visually you show up and the packaging looks the exact same as all that other stuff, people will feel like it's wrong. It'll just feel broken. It just won't perform the same way. Setting that expectation and packaging it where the jankiness is a charming, delightful thing, or like kind of expected. And this is where I get super excited about terminal interfaces. This is what I'm talking about with a terminal user interface. This is just a little GIF. Think about like your expectation when you see this. It's just novel and different. It's Martian and you don't know how fast it should be. It's like, what's the eye candy? This is different, you know? I think the little jank inherent to peer-to-peer networks, that could be the friction that like just doesn't work for people. And I think the only way you really manage that is expectations. I'm personally super into the expectations that this sets. Things should be strange, be different, but it has to thread the needle between like familiar but not familiar. That's my little extra bonus. Watch out for this. If there's something that needs to be solved, it's that. But as long as there's a really good reason to be there, like if there's something cool and you cannot get it anywhere else, the jank won't matter. The mismatch between expectations and what the actual performance is, that won't matter. This is considered the killer app. There's something you can only do on Urbit. If you have to get on Urbit to be there, then you're going to. That kind of makes some of this a moot point. So far, there isn't something created that way that I'm like, telling all my siblings, like, you have to be on this and doing this. Right now, it's small and exciting. It has longevity. Like, work on something that matters in 100 years. That's pretty cool. That's my little bonus rant there. Hope you enjoyed those things. I have ran out of things to say, so Ferb, can you tell everybody? Goodbye. He's like the smallest little meow. It's so tiny and pathetic. It's so cute. His brother, Phineas, he meows all the time. So vocal and purry. I love Give Directly. It is my #1 choice. Anytime I think about wanting to help the world, help other people in hard times, all roads lead to that. No strings attached, handing people money is the only way I know to let them solve their problems. $530 I was able to send over to Give Directly. I'm proud of having my name given to them. It's good. I'd love to double that. I need to think of the next thing. I'm not 100% sure if it's officially videos. I have something else in mind, but that's for a different time. So we're back to this screen. I just want to thank the people who've given to fund. You guys are the awesomest. Thank you for letting me give to Give Directly. I just feel great about it. I just want to do that more and more. Thanks for watching all these. Have a beautiful Urbity 2025. Bye. Hey, Ferb. Oh, gosh, do not go for that. It's Ferb. He's the size of both of them put together from earlier. Crushed it. All right. Bro, you're maximally disturbing while also making me maximally feel like if I was to put you away, I would be a bad person because you're so lovey-dovey right now. Oh, Ferb. I'm running out of my hour here. Everything is at jeopardy. All right.